We are here to help.
There are many different methods that are used to evaluate integrals. However, it is not always easy to recognize what method is best. Sometimes one method is better to use than another, even if both give you the same answer in the end. In this video, we are going to talk about when to use trigonometric substitution when evaluating integrals. Trigonometric substitution works similarly to the regular u substitution, except instead of substituting an expression for a variable u, we use a trig function. Let's look at some of the scenarios in which it is best to use trig substitution. One of the circumstances where we typically use trig substitution is when a difference of squares of the form b squared minus ax squared is embedded in the integrand. Another is when a difference of squares of the form ax squared minus b squared is embedded in the integrand. Another is when a sum of squares of the form ax squared plus b squared or b squared plus ax squared is embedded in the integrand. We also use trig substitution if a polynomial such as ax squared plus or minus bx or ax squared plus or minus bx plus or minus c is embedded in the integrand. In this case, if we complete the square, we will obtain one of the other three forms. Now, let's look at how we use trig substitution. Consider the following example. Our goal is to substitute x for a trigonometric function. But how do we know which trig function to use? No matter what integral we are evaluating, when using trig substitution, we always start by drawing a right triangle and writing out the Pythagorean theorem. We are going to use the Pythagorean theorem to label the sides of this triangle based on our integrand. Notice that in this example, our integrand contains the expression of the form b squared minus ax squared. If we rearrange the Pythagorean theorem for either a or b, we get an expression similar to what we have in the integrand. The equation we obtain from rearranging the Pythagorean theorem tells us how to label the sides of the triangle. If we let side a be root 9 minus 4x squared, then side b will have length 2x and the hypotenuse will have length 3. Now, we choose our reference angle theta. From here, we need to express x in terms of theta. From the triangle, we can see that sine of theta is equal to 2x over 3. If we rearrange this, we get 3 over 2 sine theta equals x. Now we need an expression for root 9 minus 4x squared in terms of theta. We also get this from the triangle. As we can see, cos of theta is equal to root 9 minus 4x squared over 3. Rearranging this equation, we get what we need. The last thing we have to do is solve for dx in terms of d theta. To do this, we take the derivative of x with respect to theta and isolate for dx. Now we can substitute everything into our original integral to make the change of variable from x to theta. Before we move on from this step, we have to make sure that when we divide by cos theta, that we are not dividing by 0. To check this, we look at the restrictions on theta. These restrictions come from the square root. The expression underneath the root must be strictly greater than 0. If we solve this for x, we get that x must be between negative 3 over 2 and 3 over 2. Since x is equal to 3 over 2 sine theta, we can replace x in the inequality and solve for the restriction on theta. Cos theta is never 0 within this interval of theta, so dividing by cos theta in the integral doesn't mean we are dividing by 0. We can now continue solving the integral. We can't leave our answer in terms of theta, since we are not evaluating a definite integral. To solve for theta in terms of x, we use the equation 3 over 2 sine theta equals x. And the final answer is 1/2 arc sine of 2x over 3 plus c. Let's look at another example with a different expression. Consider the following integral. As we can see, this integral contains a sum of squares. As before, we start this problem off by drawing a right triangle and writing the Pythagorean theorem. If we rearrange the Pythagorean theorem for the hypotenuse, we get an expression of the same form as root 1 plus u squared. This tells us root 1 plus u squared will be the hypotenuse of the triangle, 1 will be the length of one of the arms, and u will be the length of the other arm. Now we choose our reference angle and solve for u, du, and root 1 plus u squared in terms of theta. Using the triangle, we get that tan theta equals u. To solve for du, we take the derivative with respect to theta and isolate for du. From the triangle, we can also see that secant theta is equal to root 1 plus u squared. Now we can transform our integral from u to theta. Once this integral is solved, we still have to substitute back in terms of the original variable x. Now let's look at an example containing the expression ax squared minus b squared. Once again, we want to start out by drawing a right triangle and writing the Pythagorean theorem. Rearranging the Pythagorean theorem for one of the side lengths, a or b, will give us the desired equation. Comparing this to what we have in the integrand, we can see that one of the arms of the triangle will have length root 25x squared minus 4. The hypotenuse will have length 5x, and the other arm of the triangle will have length 2. Then we choose our reference angle and solve for x, dx, and root 25x squared minus 4 in terms of theta. Now we can substitute everything into the integral and simplify. And our integral is now ready to solve. We are not going to solve this integral, but once it is solved, in terms of theta, don't forget to substitute back in terms of the original variable x.